So a few words to myself first. So I am starting I will be leading the computer graphics group at IDEAS starting this summer. I'm coming from NJIT, New Jersey Institute of Technology, where I'm also doing research as a professor in computer science, working on computer graphics. And I'm working on computer graphics academically for more than 20 years. I'm very passionate about that topic. And today, I want to talk actually about one specific branch of graphics in combination with AI, a topic which is very, very timely now, and I hope it also correlates with the background of our guests today. And I want to present some developments in that area. And this talk was scheduled for 45 minutes, so I hope I'm not going over time, and we can discuss on the end if there are some questions. But first, before we dive into it, I would like to make a definition what is computer graphics from the academic point of view. When we look up the definition in a dictionary, it says computer graphics is the use of computers to synthesize and manipulate visual information. And I personally would extend this definition by adding visual and geometric information, which also constitutes a big part of the research and also applications in computer graphics. So, and humans are very visual creatures, actually. So if you ask why we need computer graphics, because about 30% of a human brain is dedicated to visual processing. So in other words, most information we actually take into our consideration, take into our conscious, goes through the eyes. Eyes are the highest bandwidth port into the head. And that's why we have the saying, one picture tells more than 1,000 words. And that's actually what we want to do in graphics. We want to create visual content, including various types of information. And generally, we could, at some level, divide graphics into 4 major areas, where we can say there is the rendering, which is computing 2D images from 3D content. There is modeling. Modeling is actually the creation of the 3D content. Animation, which means moving the content, simulating how the content moves over time. And imaging is actually, on the end, dealing with the 2D images we create. It overlaps with image processing. So this crude, very old, simple graphics should depict the 4 tasks of computer graphics. So we would like to create a 3D model, including the lights, place a virtual camera, and then create the image using the camera, which gives us the 2D image on the end. So computer graphics is I call it sister discipline of computer vision, where in computer graphics, we want to generate content, synthesize content using rendering, animation. Computer vision tries to do the opposite, the vice versa process. So extract information from visual content, usually given as 2D imagery. So the analysis of and reconstruction of 3D content from images and understanding of those images, this is the task of computer vision. And here, computer graphics and computer vision are like these 2 disciplines working very closely together and overlapping in many areas, and also overlapping in the scientific communities. And here I would like to try to show applications of graphics, practical applications. I know this slide is a visual overkill, but it's intended to be, because graphics is a field which is pretty wide, has a wide applications in many other fields in industry and also other sciences. especially in engineering. So the applications are wide, from computer games over special effects, virtual productions in movies and in advertisement, going to engineering areas, automotive and aerospace, manufacturing, scientific visualization, medical visualization, and even quite an overlap with robotics. So those are fields we would like to work together or do it already. So the foundations on graphics, and here's the famous octopus. I don't know how the animation plays over the online connection. Is the animation fluent?
Yes.
Okay, great.
Kind of okay.
Kind of, yeah. Well, I mean, that's unfortunately a little bit of constraint. So on my screen, it's fluent. So this is a real-time rendering of this octopus. So in other words, this is not a pre-computed animation. It's a okay. Let me fix that. So this is there it is. So this is a real-time rendered content as a PowerPoint plugin using Web 3D. So as you can see, I can rotate it, look at it from different sides and so on. It's not pre-computed. So part of computer graphics, especially in the context of computer games and pre-visualizations in visual content production, is real-time rendering. And the foundations of graphics are also widespread. So this is, of course, mathematics. Actually, graphics is a very mathematical scientific field. We also incorporate parts from physics, sampling theory. We also research human-computer interactions, so where we overlap with other researchers, and incorporate artificial intelligence in our research. Of course, this is a subfield of computer science. So we do extensive programming, work with input-output device, and some graphic-specific programming languages. And graphics also overlaps or let's say collaborates with art and psychology. Perception of visual information is a part of graphics. We often use in knowledge from psychology of perception of color, stereo, motion, in order to create realistically looking imagery in graphics. And of course, we also work with art and design because the content we want to visualize is also important. It matters. It's a very creative field. So that was my brief introduction to computer graphics. Before I go ahead, are there any questions at that point? Okay, so let me go ahead and swap the topics now. I want to give you a brief background on my neural networks here. So everybody knows the term neural networks, artificial intelligence using neural networks, and machine learning. Today, I want to give you a lecture on neural networks, very brief and very fast, and I hope it gives you the background for the ideas I want to present later on. The neural network is composed of neurons, and that image should depict a neuron. Okay, a neuron has an input and an output, and something happens in the neuron. And it only gives us an output if something has actually occurred within that neuron. And neural networks are composed basically of this simple type of neurons. And we can denote it as an input, output, and a neural node. And the neural node itself is actually a very simple mathematical operation. We can think about it as a multiplication combined with some additional, we call it non-linear term, which we call an activation. So the first part is just a multiplication, just a simple mathematical operation. Actually, it's a multiplication and addition. and it's wrapped by a so-called activation function. And that might sound a little bit abstract, but when we go ahead, we can see the output of a single neuron with a simple so-called ReLU activation is a very simple function. So we all know from the high school, okay, that y is a function of f of x, and that f is our neuron. So here is the x-axis, and here is the y-axis. And the output is just this simple graph, which we see is a line with a kink. We have here a kink. And that's it. It's a line. So that's the output which a single neuron can give us. So if x is the input, y is the output. And why I'm showing you that, I would like to explain you how a neural network actually works, at least from a certain point of view. So using this single neuron, which can produce that simple output, which is a line. So the line can change. So the slope of that line can change, and the position of that kink can be also shifted. But that's actually all it can do. We can use that neuron.
Spróbuję, znaczy, może to zrobię jakoś tak, bo... No dobra, nic mówię się.
Maybe you can mute your microphone over there.
Jak się nazywa w tym projekcie, no to on po 4-6 godzin, to nie proszę.
Can you please mute your microphone?
Yes.
Okay, thank you. So I still hear a lot of voices.
Miłość. Wyżej, spokojnie.
Okay, so that simple neuron can now be used to approximate functions. Okay, so let's look at the blue function. It's a mathematical function. Essentially, y equals here x sine of x. Right? This is this blue function. And we want to approximate. What does it mean? We want to copy that function, but using our neuron. And that's what we do. And since our neuron can have only one kink, a piece of a linear, and two pieces of linear of lines, this is the best approximation of this x sine x function with a single neuron. Well, we can argue if it's a good approximation. I think it's a pretty good approximation for a single neuron. But maybe it's not good enough, not for our purposes. And so what can we do to improve that approximation? Any suggestions from the audience? Now you can unmute your microphone. Yeah, I heard it. Add more neurons. And exactly that's what we can do. We add more neurons. So we add one more neuron. And the second neuron does exactly the same thing. So now we have two kinks and three pieces of a line. And now we can approximate our function with two neurons. And as we see, the approximation is better. So the orange line nestles to the blue line more closely. And yeah, because we are smart, we can add also three neurons. And now we have three kinks and four linear pieces of a line and so on. And as you imagine, we add more and more and more neurons, we get a better and better approximation of that function. And because we know mathematics, we could compute here a limit. And when we add infinite number of neurons, obviously, we perfectly approximate that function. And we can add those neurons in a so-called one hidden layer. So this is the so-called input layer, the output layer. This is just the x, this is just the y, and the whole thing approximates the function f of x. And we have one hidden layer of neurons. So now we can also play the game and add more layers, more hidden layers, and put the neurons after each other. And that's like what we started calling deep learning. Deep learning is adding more and more and more layers. But the game is the same. So adding 2 additional neurons, we can approximate the function with 2 kinks and 3 linear segments, and so on and so forth. And we can combine it. We can add both hidden layers and more neurons in each particular layer to get a better and better approximation of a function. So, and that's the first part of my recap here on neural networks. We can think of a neural network as a function approximator. And in fact, with sufficient number of neurons, we can approximate any function up to a certain error. The question is how big is should be or could be the error we accept. Nonetheless, from that point of view, a neural network is nothing else as a function approximator. In this case, piecewise linear. We can use, of course, also other activation functions and so on. And the truth is, one hidden layer is enough to represent an approximation of any function to an arbitrary degree of accuracy. So why do we go deeper? Why do we go into depth? Because first of all, we would need exponentially more neurons when we go into the width. So it's better to go to the depth. The number of neurons is smaller to get a better approximation, which also correlates with an overfitting of a signal. So meaning approximating the signal very exactly, which not in any case is the desirable goal. But that's other topics. I don't want to go there. I want to go now to the so-called neural fields. Neural fields, let me give you a definition. A field is a quantity defined over all spatial and or temporal coordinates. So what does it mean? We all know fields because we are surrounded by fields, by vector fields, by scalar fields. Okay, a vector field, like a gradient field, is a field. An image is a field because it maps spatial coordinates to RGB coordinates. Okay, mathematical surfaces, curves, can be interpreted as fields. Then we can also interpret geometry as 3D signed distance fields. I will come in a couple of slides to that topic. Audio signals are fields. So as you see, almost everything which we want to interpret mathematically as a function with an input and an output can be seen as a field. So let me extend the definition. A neural field is a field that is parameterized fully or in part by a neural network. And now these two parts I presented you come together. Now we can take our neural network, which is an universal function approximator, and a field, which is a function which maps one domain to the codomain, to the range of a certain dimensionality, in the simplest case, just 1D to 1D. That's what we have seen. And this network is, in these terms, a neural field. And what's so interesting about it? The interesting part is that we only need a small number of samples from our function, which we want to approximate, in order to get a nice representation of the function. So in other words, when I approximate the x sine x function here, you can say, yeah, that's pointless. Why do you approximate a function which you have an analytic formula for, x sine x? Why do I want to approximate that function? Well, to be honest, just to show you how it works. But I could just sample a couple of samples from that x sine x, like those points here, plug them in one by one into my neural network with a single input x and a single output y, one by one, not all together, okay? And the neural network will learn to approximate the function. And on the end, I can use the function as a replacement for x sine x. So I don't know, I don't need the x sin x anymore. I can use the neural network. And the good thing is it also keeps a lot of properties of that function, including the differentiability. And those neural fields are, of course, more flexible. So we can use 2D inputs and map them again to 2D, to a vector field, like the magnetic field. Or we can map them to flow fields of fluids in 2D or in 3D. And as you can think, that scales up. So we can, for example, use it to create sign distance fields. So what are sign distance fields of geometry? We map the position in space, x, y, z, or here it would be just x, y, to a distance to a surface. Okay, so here every point gives us a distance to a surface. So the color tells us the distance. Okay, the more intense the color is, the closer we are to the surface. The surface is the black line. And when we are inside an object, we put it at a negative distance, and we are outside, we put it at a positive distance. And on the end, on the border between those negative and positive space area or space volume areas, lies the surface that allows us to represent 3D geometry in a network. And again, we only need a couple of samples to train that network to represent it. And that scales to very many applications. Also, other scientific areas use that. Here, for example, geospatial applications. So in general, we could map it here to any dimensionality we would like, and that must not be 2, that can be also some other dimension. In other words, neural fields is a tool to approximate high-dimensional functions. So, and that area of neural fields is at the moment very, very actively researched. So there are actually hundreds of papers a year appearing on that topic. So here we see papers on neural fields since 1989 to 2021. And we see this is an exponential growth. And it's overwhelming, actually, also in science. I have never seen so many new ideas and papers published on a topic as it happens now with neural fields. So, but neural fields are not necessarily super new. Here's a paper from 89, which introduced already the concept of encoding field function using a neural network. Unfortunately, end of the 90s, neural network was still not very large and powerful, especially due to the hardware. GPUs popped up end of the 90s. GPUs came actually from the graphics. We wanted to do real-time rendering, and that's why NVIDIA and a couple of guys over there started producing chips which do what graphics needs. Graphics needs simple mathematical operations, but a lot of them, and especially in parallel. And that's what the GPU does. GPU is a massive parallel processor of simple mathematical operations. And then after a while, people realized, oh, that's exactly the same thing what neural networks are. Simple mathematical operations processed in parallel on a massive scale. And that's where graphics actually contributed, or how graphics contributed to the big boom of deep learning like around 10 years ago. So the original paper proposing the field idea to approximate field functions using neural networks is from 89, and rendering techniques. So a few words to the terminology. I'm not going to bore you with this theory the whole presentation, so I'm going to show you some nice pictures on the end too. But first, these neural fields are very often also called implicit neural representations because they implicitly learn the function. Sometimes they're called coordinate-based neural networks. And they're called coordinate-based because those networks learn the function, but the network itself takes only a single sample from the function and outputs a single output of the function. So they are coordinate independent. They are not like convolutional networks when you think about them, when you know what I'm talking about. So the input is not fixed. The input is just a point from the function, and the output is also a single output corresponding to that point of that function, which also means when you train that network, you can treat it as the function itself. It's a replacement for your function. And that's why they're called coordinate-based networks. And often they are now called also nerves. Actually, this is not correct, but people call it like that because nerves is a very specific field of a very specific neural field used for, and that's what I want to talk about next, used for rendering and inverse rendering. Yeah, but I would say in general context, often people just say nerves to those implicit representations. So maybe one more word. Why those neural fields are so good? I already told you they are coordinate-wise approximations of complex functions, and we don't have to have the function itself. We just need a couple of samples from that function. So representation of signals in mathematics, engineering, and scientists, it's a very important thing to represent and deal with signals. Can be continuous, like our sine function, can be discrete as a couple of samples. And in computers, actually, all of the signals at some point are discretized. And now with those neural fields, we can have neural representation of functions. So in other words, we over sample a network, and the network itself becomes just a function parameterized by the network parameters, which are in the neurons. And the good thing is they can be evaluated and differentiated at any location, like continuous signals. And they can be learned from sampling continuous signals or from discrete signals or from any sampling you can get, like from point clouds, scans, and so on, photographs. So let me now come to neural radiant fields which became very famous in graphics. The original paper published 2020, so it's already 3 years ago. And the idea was great. It was groundbreaking. The idea of neural rendering. So let's take a couple of photos and reconstruction of point clouds from a couple of photos, which is called photogrammetry. It's nothing new. We can do it in the theory, we can do it probably since Gauss, but in practice, we can do it robustly in production quality for 15 or almost 15 years, I would say. Like deep synth and applications where you plug in a couple of photos of the same scene, and from that photogrammetry, we can reconstruct the point cloud in front of the photos. Now, the idea of those fields is to reconstruct the whole scene. Do not reconstruct just a couple of points. Reconstruct the whole scene, including the lighting. That's the idea of neural rendering, inverse rendering, based on nerves. And we can obtain very high quality reconstructions. And that example from NVIDIA, published last year, CVPR, is real time. So essentially, it's real time. It happens. You take your photos with your webcam, and in real time, the computer reconstructs you the whole scene from a few shots. So what's the idea here? What is the field? The field is a function which maps XYZ position, the direction of the vector, viewing vector, giving two angles. We only need two angles to represent the direction of the vector in 3D space, to RGB plus the density. And photogrammetrically, essentially, we can get a couple of points in space, and we feed those couple of points in space, including the information, into a network. We train it, oversample it, and the network learns the whole space, the volume. So it knows at every location in space what's the RGB color and what's the density at that particular location. So now, having that network, we can place virtual cameras everywhere in space and render, inversely render, synthesize a new view from a camera which has not been given during the training process. And they turned out to be pretty interesting because of the quality. I don't know how this animation plays over the internet. Is it fluent?
Quite okay.
It's okay. All right. So all those scenes are, all those objects are reconstructed from a couple of photographs, and nerves go further. We can also change the appearance of objects, detail, texture. We can relight. So once you have captured the scene, you can change the light position virtually, just given the neural radiance field you have captured from a couple of photographs. So relighting is a topic, and I will show you a couple of more of applications. So here, a scene reconstructed from a couple of photos, as you can see, including gaseous phenomena like smoke. It's a great representation for volume data. So this is a shot, can be using nerves, now created, well, by very amateurish tools. Okay, we can extract normal fields, so the normal vectors on the surface, depth fields from photos. So depth fields, so what's the distance to the camera, and many more tools. So neural fields have also a lot of application in other sciences and optimization, topology and optimization, tomographic, so the radon transform, reconstruction, astronomical informametry, and contact dynamics, and many more. Actually, physics-informed neural networks are also a big topic in those areas. So one more topic I want to cover are sine distance fields. They also, so this is like another application of neural fields. We have the nerves, neural radiance fields. Now we are talking about sine distance fields. So those are those fields I was talking about, where we take 3D space, and at every location we store the distance to the surface of interest. And if it's outside, it's a positive, and if it's inside, it's a negative. And the border between those two gives us the surface, implicit representation of a surface. So why is it interesting? Well, first of all, because we can reconstruct surfaces now from point clouds. We can take again a point cloud. It can be a laser scan. It can be photogrammetric reconstruction from a couple of photographs. Boom, plug them into the training process of a neural field, and you get a sine distance field. And that gives you here the layers constitute like the distance from the surface. And this is a very interesting representation of geometry, which gives us also new possibilities. For those of you who have some background in machine learning. Machine learning is very often about classification. We can also use the paradigm of classification to represent a surface, actually as the so-called decision boundary of a classification problem. We can say all points inside is one class, all points outside is the other class, and the surface of interest is the actual decision boundary. So those networks are called the occupancy map networks. It's essentially the same thing as the regression networks, because this traditional or this direct representation of sign distance fields, that would be regression networks. So why is it interesting in modeling in graphics? Because we can now train a network not only on one single object. We can train a network on a whole bunch of objects of one class. For example, let's say I have a database, ShapeNet, of 10,000 chairs. So now I take the 10,000 chairs, create point clouds of them, sign distance fields, and I train a network. And the network stores inside a function, a mapping for all 10,000 chairs, okay, in one single network. Of course, we enhance it a little bit. It's a so-called auto decoder, not an auto encoder. It's an auto decoder. We add some signatures into it to identify particular chairs, but it gives us a latent space where we can morph objects, we can create new objects, and we can analyze objects. So it gives us a tool for the latent space exploration for specific types of geometry. And of course, also in future, hopefully, a tool to generate new geometry, semantically enriched new geometry. Semantically, I mean that there might be a certain type of geometry, like this vase, for example, or that one, but it can have a different number of handles. Here we have 4 handles, here we have 2 handles, here we have no handles at all. So each color here corresponds to some functional part of the geometry, but geometrically itself, it's very distinct. So it's very difficult to compare that one to that one geometrically. When you do it point by point, it won't work, because here you have 4 handles and here you have no handles at all. So here, this morphological or topological differences of geometry, very difficult to handle mathematically, come into the play. So where we have also applications of nerves and sign distance fields in graphics, manipulation of objects. So here, for example, retargeting, giving a video sequence, we train a network, adding additional knowledge as a skeleton, which is fit into the network. It recognizes the person and it can retarget the person in the video. Various appearance, I will go, and movements can be transformed from one object to another object. Yeah, let me skip that one. Rigid body, mesh deformations. So the deformation and animation, of course, is an important topic in graphics, and that gives us a new tool. And here is a very nice one, especially in the context of effects of video production. It allows us to disentangle spatial and temporal movement. So I will play you the first video, and it should be jaggy. It's a very jaggy video with a couple of frames. It's actually not a video, just a couple of bracketed frames. And from that one, we can, for example, fix the time and extract the motion of the camera. Okay, or we can fix the view. So now the camera view is fixed and we can extract only the motion of the people. Or fix, or have a space-time interpolation, so between all those frames, which were actually missing in the original video. So Last few words on generative modeling, because this is like the hot topic in many terms. I tried to sell you, it's not a hot topic anymore. Now we are on neural radiance fields. But still, generative modeling is a new tool coming up, and it can be used with neural radiance fields or neural fields in general together. So generative modeling is about training probability distribution from the data and generating new data. So all those applications of neural fields can be combined with general modeling, exploring the latent spaces of those coordinate-based networks, combining it together. Here, for example, recent paper, CVPR 22, the famous or infamous T-pod, Utah T-pod in computer graphics. He generated as new variations of this 3D object. So this is our recent work, SIGGRAPH Asia last year, generative modeling of apartment layouts based on data and based on expert knowledge. So here we combine data-driven learning with input from the user to synthesize new outputs, new apartment layouts, which should be better or are in many terms better than just data-generated layouts. All right, let me skip a couple of slides here. So on the end, nerves have already become part of digital production pipelines on a, I would say at that moment, on a pretty experimental basis, but I believe this is the future. I believe that way how ChatGPT or actually GPT, by the way, our work here with those layouts uses GPT-2 as a foundation for learning the layouts. So those layouts are trained using a GPT-2 model trained on natural language as a foundation model to create architecture. So yeah, we can combine a lot of information from different domains if we do it properly. And this is by far not trivial. And those are research problems in graphics in combination in NI, problems in rendering using nerves, problems in modeling using signed distance fields, and the combination of both with generative modeling. So at IDEAS, we want to do neural rendering, neural modeling, and neural simulation and animation. And for those students who are watching, hopefully, so if you like to be part of the group, you are welcome. You should have some math affinity because graphics is a math. I wouldn't like to say heavy because heavy sounds so heavy, but if you like math, it's light. So you should have some math affinity. If you don't like math, probably you shouldn't do that. Some programming skills, you should be motivated. You should be passionate in the best case, but you don't have to. You can do it also for money. I'm fine with that. The point is, you don't have to know all of those things. You just have to be curious and open to learn a lot of new things. And you will learn step by step. Nobody expects from you as a fresh PhD student that you know and understand all of those things. You should just have some interest, maybe a little bit intense interest in those topics. And what we offer is a professional environment in international scale research. And of course, our goal is to be present in top-tier scientific communities. So our major goal is the ACM SIGGRAPH conference, which is the world's most famous, biggest, and greatest conference in computer graphics. But we also look into the CV and machine learning communities and try to pair up with people, or also, as I already said, there is a certain overlap happening in those areas. So all those are top conferences in the world on those topics, and that's what's our aim. And yeah, you are invited to join us on the journey. Thank you. Any questions at that point? Any questions from the online audience? Oh, sorry. Yes, there was a question. I've heard that.
I have a question.
Yes.
So when do you think there will be kind of a DALI for 3D objects?
I didn't really hear the whole question.
So DALI, so this is text.
I know DALI, yeah, but what is the question about DALI?
Yeah, so when there will be a DALI for 3D objects?
Soon, we want to make it. Well, I mean, I didn't mention that, but we can also collaborate with R&D departments of industrial players. So one of the project of an architectural design was a collaboration with Adobe Research. And I think we were open to collaborate with various, I mean, also especially with Polish players on that market. So in graphics, we have a lot of ideas. And as I already said, often we need to be constrained by practical problems in order to implement those things.
I have a question about the genuine representation, like for using nerve. You said that there can be some pictures that can create a whole visual space. So how true can it be? For example, it can be used in crime scene detection or something like that. But if represents something false, so like what is the degree of right representation, true representation?
I have a lot of interruptions in the question, so let me repeat it. I understood. So what's the accuracy of the nerve?
Yeah.
In a nutshell. So I think it's not very good, but for visual content, it's enough. It's fair enough. Of course, we can. I mean, it depends on the sampling. It depends on the network. It depends on the activations. So there is a lot of parameters and hyperparameters which needs to be tuned, and that's the hard part to get it into the reasonable quality. So in theory, it's simple. In practice, you spend hours, days, and weeks in tuning those things. So I would say depends on the application and depends on the data. And of course, on the skills of the programmer who is working with it. Does it answer the question at least a little bit?
Yeah. Sure.
More questions?
Tomek?
Hi. Yes, thanks for a very good overview of neural rendering. Yeah, do you hear me well? Is that okay?
I hear you well. Yeah.
Oh, okay, excellent. So thanks, Przemek, for this great overview, and I'm really happy that you're joining IDEAS since the topics are very close to my heart as well. Although it's a tough challenge actually to attack all of those difficult tasks that you mentioned. Out of curiosity, since there is so much research going on in specifically neural rendering and nerves, and there's not a single week without a paper on how to make them more efficient, more precise, easier to handle. We've seen this incredible increase in the number of papers you showed in this presentation.
Extremely.
What is your maybe not secret sauce, but your kind of approach towards attacking this challenge of publishing in the field? How do you plan to, distinguish yourself or differentiate yourself?
That's a great question. That's a great question, Thomas. So, well, I mean, I don't want to. First of all, I don't read all of those papers because that's not true. I don't read many of those papers because many of those are some incremental improvements, right? And you can do a lot small incremental improvements at the moment in that area, which are still interesting and can be published. This is one thing. I try to focus on more on the milestone or seminal papers. That doesn't automatically mean that I'm publishing or aiming at milestone and seminal papers. Actually, I'm aiming at them, but it not always happens. I think there are now tools, AI tools, like Semantic Scholar, you probably know, which help you filter out papers. So, of course, it's a change. To me, it's a change. During my PhD time, I knew all the papers in my area. Now it's impossible because there are so many, right? So I try to filter them. I try to scan them. I try to focus on them. And of course, I also rely on those which are cited a lot and which introduce some significant seminal improvements. I don't know if it answers your question. So this is like the first part of the answer. How do I deal with this vast amount of papers? So the other one is, the question is, how do good ideas come up? Okay. Some come up, obviously. Some come up, some ideas might be or could be inspired by previous work. And some ideas come out of necessity. So you have a problem you have to solve, let's say from a virtual production company, and they want to solve a problem. And then you have to be creative. And this is where often good ideas pop up. There's a second part. And the third part, if you ask me, how do I plan to approach this vast field, is, of course, it would only work if we find enough great PhD students, passionate PhD students, who are interested in that field and who want to work. It's not a one-man job. Does it answer your question?
Thank you. Yeah, thank you. I mean, I think it's a great opening for the more follow-up discussions when you land at ideas, but I'm happy to continue those. Thanks so much again.
Thank you. More questions?
So if there are no questions, then thank Przemek for this.
Thank you. I just wanted to ask on the end, do we still have our guests here? Did they follow the presentation?
Yes.
Okay, great. Because I focused it a little bit on potential applications in digital production areas, and especially here that might be interesting. This is there is a page. There's like a newspaper-like page called neuraldistancefields.io. It's an independent page which brings new articles, applications from that area, and one recent one is about revolutionizing virtual production, and it maybe it's worth having a look at. Okay, thank you.
Thank you. Thank you.
Thanks so much. Bye.
Thanks. Bye-bye. And see you in Warsaw soon. And for those PhD students or potential PhD students or researchers who are interested on the topic, please feel free to contact me. The more concrete topics in the computer graphics group will go online on the IDEAS page probably tomorrow. And if you have your own topics you want to suggest in that area, I'm also open to those. So feel free to contact me. You will find, just Google for Przemysław Musialski, and you will find my webpage, and you can send me an email. And you are free to get in touch with me, and I will be really happy to have as many of you being interested in a topic as possible. And one more time, don't be scared and don't be afraid. Nobody knows everything, and nobody expects from you to know everything. And it's a learning process, and that's an actual task. That's the goal. That's the goal of the doctorate. It's a learning process to become an expert on a specific topic over a couple of years. So you are welcome, more than welcome. Feel free to contact me. Thank you.